Welcome everybody. This is Mr. Ndabezita, and I thought that we should try and look at calculus. So this is done on behalf of the mother of my child, as we did previously with mathematics. She's a animal scientist, so they are dealing with a little bit more complex mathematics, so she needs to be enlightened when it comes to this. So she didn't do pure mathematics in high school, so I thought maybe I should just give you something that might be of help. So we will be using Thomas Calculus, the 13th edition. So I don't know whether she will understand this is highly complex mathematics, but I thought I should just deal with the best of the latest version of Thomas Calculus. So I have some slides that which I thought would be very helpful in explaining to us, or specifically to her, exactly what transpires in mathematics. So throughout many years in this field of mathematics, doing calculus 1, 2 and 3, I learned that understanding the language of mathematics plays a significant role. You need to know the rules, you need to have an underlying understanding of what mathematics is about, the relationship that are happening between the numbers, and what the definition truly entails. Without understanding the definitions as a template from which you can build on, you will be incredibly confused in mathematics. So without any further explanations, this is the opening slide that we have. We gave the introduction on this one, and then we will be dealing with the very first chapter in calculus by Thomas, which is the functions, and we will just have an overview reading as to what is happening here. So an overview, he says that functions are a fundamental to the study of calculus, so they play a very significant role. You cannot separate functions from calculus, they are inseparable. In this chapter, we review what functions are and how they are pictured as graphs. So this is just basically saying that a function it's a relationship. This is what a function is. A function is viewed or understood in mathematical context as a relationship between two things. So in mathematics, we are dealing with the x and the y as the alphabets attached to the input values and the output values. So you have a function which is a relationship, and this relationship can also be pictured in a graphical representation. Very important. So when you are looking into a graph, any graph that you can think of, you are basically looking at a relationship that is happening between the x and the y coordinate. Very important. Or the relationship happening between the values of x and the values of y. And there can be different types of relationships. You can have one-to-one, one-to-many, many-to-many, but we will look into that. But just the basic understanding that a function is a relationship between two things. Very important. And we can represent this relationship in a graphical representation. All right, how they are combined and transformed. So we can combine these functions and we can transform them by enlarging, translating, rotating. Many things can transpire, and ways they can be classified. There are different classes through which these functions can be classified. We review the trigonometric functions, and we discuss the misinterpretations that can occur when using calculators and computers to obtain a functions graph. So there are many misinterpretations that can occur when somebody maybe tries to calculate something or punch something on a computer in order to obtain a functions graph. So as we said that these functions can also be represented in a graphical way of approach. So the real number system, the Cartesian coordinate, and the straight lines, circles, parabolas, and ellipses are reviewed in this appendices. So we will be looking at a variety of this, and all these things are functions. Remember, they are represented in a graphical representation. It's very important that we understand that the coordinate system, the Cartesian coordinate system, is it's a, let me just put it in this way, it's how do I say this? All right, it's just a line. We have the vertical and the horizontal lines through which we can represent a function on a coordinate system. Very, very important that we understand that. And then on this Cartesian coordinate system, we can represent a function as a straight line, a relationship that shows a linear relationship between the values of x and y. We have a circle that is represented on a Cartesian coordinate, and we can look at the relationship between the x and y, the circular shape that is formed, which we refer to as a circle, with the radius and everything that is embedded in that. That's a relationship that you are looking at. Whatever that is represented in a circular form, it's a relationship between, because you have the values of x and the values of y mapped with one another in order to form a circular shape. Very, very important that we understand that. And then we also have a parabola, which is also a relationship that gives a certain form of a graph that is different from the circle, different from the straight line and all that. And we also have the ellipses, shape. We have something like an oval shape of what we refer to as an ellipsis, and all of those things will be reviewed in this 13th edition of Thomas Calculus. So we will be adding even more graphs that are not even spoken about yet. Here he was just referring to just a few of those which can also be viewed as a function. Remember, this is very, very important that we understand that. Okay, this is just the slide trying to give us an overview of what a function will be all about. All right, and then in 1.1 we will be looking at functions and their graphs. So you have a function, which is a relationship, and you want to see how this relationship will behave when you represent this relationship in a graphical way. This is exactly what we are saying here. Functions are a tool for describing the real world in mathematical terms. So we are in this planet Earth, and we want to do what now? We want to describe the real world using the mathematics. Why things are situated the way in which they are, why certain objects behave in this way. So we try to apply mathematical analysis in order to understand why things are in that way. And once we understand this mathematical model that we have written, that we have understood, therefore we can build from there, moving forward, why things are the way in which they are. Understanding the fundamental laws of mathematics allows us to manipulate that which is visible and invisible in the world that we have occupied. Very important that functions are a tool, very useful tool for describing the real world in a mathematical terms. Very important. A function can be represented by an equation. So you can have a function, and this relationship that is happening between two things or three things or four things, you see 2D, 3D, 4D and so on. We will look at all the dimensions, but for now let's just stick to two things. You have x and y, And now you can see that this is the relationship that is happening. When X does this, this is what happens to the values of Y. So I can see how the values of X are affecting the values of Y, and how Y also affects the values of X. We can look at the forward and the reverse processes of affection between those two things. And then once we have that, we can write down a mathematical equation that will tell us, even in 3 years, 5 years, 10 years, or whatever, what will happen. We can predict the future using a mathematical equation, having understood the relationship between two things or three things or four things, how they behave. We write down a mathematical equation that describe exactly why this is so. So by writing this mathematical equation, we can even predict in the future what would happen if these would be the conditions at that time. All right. Okay, we are saying a function can be represented by an equation or a graph or a numerical table. So these are the different ways in which we can represent a function. We can represent a function by writing a mathematical equation, or by drawing a graph that tells us how these functions behave, or a numerical table. So we can have, for example, a table of values for X and Y, and we can have an equation, and we can fill up the table based on the equation that we have understood, based on the relationship that we have seen happening between these things. All right. Or we can even have a verbal description. We can just verbally say or predict what a certain function would do. So there's also a verbal way of predicting what the relationship that we are seeing in a mathematical model. All right, we will use all four representations throughout this book. What are those four representations? It's an equation. We can represent a function as an equation, as a graph, as a numerical table, or as a verbal description. Those are the four main representations of a function throughout this book. And then this section reviews these function ideas. Okay, that it's fine. And then we move on to functions, and then we will be looking at the domain and the range. What is a domain of a function? Now that we know that there's a relationship that is happening between 2, 3, 4, 5 things, depending on the dimensions of the objects of interest. Now that we can see, we know the function, having viewed that function in terms of a numerical table, an equation, a graph, or a verbal representation, then we want to know the domain and the range of this function. So let's read what Thomas has to say. And then he says that the temperature at which water boils depends on the elevation above the sea level, which is the boiling point, drops as you ascend. We are going to look at physics because she's also doing physics, and we will deal with all these things. Maybe when we have time, we will deal with classical mechanics before we can move to quantum physics, because it is impossible to understand quantum if you don't understand classical view. So we will be looking at all that, but let's just read for the sake of just gathering some information. The temperature at which water boils, okay, depends on the elevation above the sea level. All right, the boiling point drops as you ascend. We know that the higher you go, the more temperature drops. Everybody knows this. We even saw this in the movies. We know that as you ascend, the temperature drops. It becomes colder and colder as you ascend higher into the stratospheres. All right, the interest paid on a cash investment depends on the length time the investment is held. This is also true because we know that the longer you invest money, the more it will generate profit, and the lesser you invest money, it will not generate that much. It also depends on the inflation rate. It also depends on some other things, but it is interesting that is mentioned here that the interest paid on a cash investment depends on the length of time the investment is held. Okay, the area of a circle depends on the radius of the circle. So remember, the area, the amount of space an object will occupy, is dependent on the radius. And this is true because we know that for a smaller radius you have a smaller area, and for a longer radius you have a much bigger area. So the area of a circle is much dependent on the radius. Remember, the distance from the center to the point on this circumference. You see, when you are somebody like me, you have so much understanding. Okay, that's fine. Let's continue on this. They say the distance an object travels at constant speed along a straight line path depends on the elapsed time. Okay, we will look at speed and velocity and time just to define all this so that you understand. In each case, the value of one variable quantity, says y, for example, depends on the value of another variable quantity, which we might call x. Very, very important. The relationship, the function from which things has to transpire. We spoke first that when the temperature of a boiling substance depends on, they said that it depends on, what did he say here? The temperature at which water boils depends on the elevation above sea level. So there's a relationship that is happening here. The radius, the area depends on the radius of a circle. So there's a relationship that is happening between two things. We are trying to emphasize the concept of a function here. So there is an interconnection that is inseparable that is happening between two things. And these two things need one another in order to survive on, or in order to execute a particular job. So you cannot separate the radius whenever you want to calculate the area of a circle. So the area of a circle depends very much on the radius. You remove the radius from the circle, you are dealing with something else. It's just something else. So what we are trying to stress here is the function relationship that is happening between two things. In all of these cases, the value of one variable quantity, which we can say it's y, depends on the value of another variable quantity, which we might call x. Very important. We say that y is a function of x. So y is a function of x simply means that there's a relationship between x and y, and the value of y depends so much or functions so much as a result of the value of x. You are functioning the way you are because of me. So this is to say I am having an impact on you in order to behave the way in which you behave. This is exactly what a function is. It's a relationship between two things where the value of x is mapped exactly to the corresponding value of y. If we use the alphabets x and y here, or if we use p and q, we will stress this in terms of p and q. Okay, let me just have a pause. Let me just go see something and then I will be back. All right, let us continue in what we have been saying. So we say that y is a function of x, and we write this symbolically as y equals f at x. Y equals f of x. So what does that mean? It simply means that y is dependent on the values of x. y is equals to the value of x at that point. So we are saying when you have a function that, for example, you have represented in a mathematical equation, since this is an equation, you have an equal sign. So in order to find the value of y, you have to plug the value of x on a function, and whatever that you find there, then that is equals to the value of y at that point. Suppose that you have a value of x that is 2 and you have an equation that is maybe 2x plus 2. So where you see x, you plug in 2. So you will have 2 into 2 plus 2, which is 6. And that value of 6 is assigned to y. So when y is 6, the value of x is 2. So we are saying there's a relationship at that point where the value of x is 2 and the corresponding y value is 6 as a coordinate, because a coordinate requires the value of x and y. Alright, that is fine. In this notation, the symbol f represents the function. This is exactly what we've said. The letter x is the independent variable representing the input value of x, and y is the dependent value or output value of f at x. So what are we saying there? We are saying that because you are an independent variable. An independent variable is a variable that other variable depends on. In this case, x is independent, therefore it simply means y depends on what the value of x is. So if the value of x is 2, the value of y will be something, and if the value of y is minus 1, then the value of y, if the value of x is minus 1, then the value of y will be something. You are independent if you are the one pulling the strings. Because of you, the value of y will be assigned a certain value. So you are the controller of this relationship. And when you say this should happen, then that will happen to the values of y. You are independent. You are the one making the rules, telling everybody or telling y that if I am 2, you are going to be 5. And what connects this relationship in between? It's a machine, a mechanism, which is f. F is the mechanism. F is the equation that equates if the value of x is this, the value of y should be that. Just as I made with an example of 2x plus 2. So 2x plus 2, what is it? It will be regarded as a function. It's an f. It's the process that tells when I input the value of x here, then the value of y will be that. This is very important that we understand. All right, the definition of a function. A function f, so you have this machine, for example, 2x plus 3. This is what we mean by f here. So a function f, 2x plus 3, from a set D to a set y. So the set D here, for example, will be the values of x that you input into the machine, and a set of y, which will be the output when D is this inputted in a function. Therefore the values of y will be that. So a function f from a set D to a set y is a rule that assigns a unique single element y. Very important. Single element f at x is an element of y to each element where x is the element of the domain. So a function f from a set of D, the values of the input, which we can say the values of x which are independent, to a set y, which are the values of y which are dependent on the values of D, is a rule that uniquely assigns a single element to y. Remember, f at x is y. to each element of the domain. This is exactly what a function is. Sorry, let me go back here. The set D of all possible inputs, very important, the independent ones, values is called the domain of the function. So what is a domain? The domain are the values of x that satisfies a given condition or equation that should result in a particular output. So the set D of all possible input values is called the domain of the function. The set of all the output values of y as x varies throughout the domain. If you are using different values of x, minus 1, 0, 1 and 2 and so on, is called the range of the function. So the domain associates with the values of x and range associates with the corresponding values of y that you output on that machine. The range may not include every element in the set y. This is a possibility that you should know, and worthy of noting that the range may not include every element in the set y. Why? Why should this be so? That the range may not include every element in the set y. The domain and range of a function can be any set of objects, but often in calculus they are set of real numbers interpreted as points on a Cartesian coordinate line. This is exactly what we have been trying to stress. And then in chapter what, okay, this is fine. We will encounter functions for which the elements of the sets are points in the coordinate plane or in space. When we deal with mathematics and engineering, we will be dealing with spaces and everything, but that's fine because it's also a mathematics chapter. I believe as we progress in this, it will be dealt with. Now let's continue with reading. Now they say, the set D of all possible values is called the domain of the function. We have understood that. The set of all output, so the set of all possible input values is called the domain of the function. And I think Thomas is being very careful here to say that the set of all possible input values is called the domain of the function, because the function machine may give you problems if you try to input the domain that might make the values of y impossible to trace. Thomas is very careful in his wording here. For example, suppose you have a function f at x equals 1 over x, and you have a set of the domain values minus 1, 0, 1 and 2, and you want to have the corresponding y values. So not all the values of x, the possible values of x, will result in the values of y. In this case, you will have to omit the value of x that is equals to 0. So the guy is very, very careful in his wording. The set of all output values of f at x as x varies throughout the domain is called the range of the function. We have read that. The range may not include every element in the set y. The domain and the range of a function can be any set of objects. Okay, that's fine. Often a function is given a formula that describes how to calculate the output from the input values. This is exactly what we said. For instance, that is to say object in object-oriented programming. Very sorry for that. The equation A equals pi r squared is a rule that calculates the area of a circle and so on. We have dealt with that. That is fine. Okay, let's continue in our reading. Y equals f at x with a formula, and the domain is not stated explicitly or restricted by context. The domain is assumed to be the largest set of x values for which the formula gives real y values. They have to be real, which is called the natural domain. So these are natural numbers because you are using natural numbers as the set of the domain. If we want to restrict the domain in some way, we must say so. So the domain of y equals x squared is the entire set of the real number system, because this is a parabola and it's defined at every point. It is continuous everywhere, but we will deal with continuity when we get there. To restrict the domain of the function to say positive values of x, we would write y equals x squared such that the values of the domain, we only accept them as positive numbers. So this is just us restricting what the values of the inputs should be, so that we have a certain functionality that corresponds to the values of y. Okay, that is fine. And then we get to our last slide, just because this tutorial is all about just giving you an overview of what a function is, and then in the next tutorial we will be dealing with problems. So this is my son. This is the beautiful son that we have, the handsome baby with my... Alright, changing the domain to which we apply a formula usually changes the range as well. A point worthy of noting: changing the domain to which we apply a formula usually changes the range as well. We know that because remember, this is a one-to-one connection. The range of y equals x squared is, we accept elements from 0 to positive infinity. Remember, this is the range because this is the parabola. Unfortunately, I did not have time to draw on the side a parabola. You would see that the parabola begins from 0 going upwards. So we are saying from 0 to positive infinity, and 0 is inclusive. But we will deal with this in the second tutorial. So the range of y is equals to x squared, where the values of x, we only accommodate values of x that are greater or equals to 0, is the set of all numbers obtained by squaring numbers greater or equals to 2. Okay, that's fine because you will be inputting those values here, so you are in essence squaring that. So that is to say we accept numbers 2 squared, 3 squared, 4 squared, and so on. Right, and then we have what we call the set notation. So in set notation, the range is you will have these curly braces x squared such that x is greater or equals to 2, close that. These are the elements of the domain, or y such that y is greater or equals to 4. These are the elements of the range, or 4 is to positive infinity. So this is a set notation and this is interval notation. When the range of a function is a set of real numbers, the function is said to be real. Obviously, when you input real numbers, you will get a function that is also real valued. The domain and the ranges of most real valued functions of a real variable we consider intervals or combinations of those intervals. Okay, that's fine. The intervals may be open, closed, or half open, and may be finite or infinite. So as you can see here, we have a closed and an open interval, but we will deal with this. This deals with the domain and the range. More especially in a graphical representation, we can look at this, but I think we will have some time to do that. Let me not go deeper into this. Okay, a function f is like a machine that produces an output, which is y f at x, in its range whenever we feed it an input value x from its domain. We have already discussed that. The function keys on a calculator gives an example of a function as a machine. We all know that from the calculator we can find the values and so on. For instance, the square root of x key on a calculator gives an output value, the square root, whenever you enter a non-negative number x and press this sign. All right, that is fine. A function can also be pictured pictured as an arrow diagram, and this is the diagram that we have on here. Each arrow associates an element of the domain with a unique or single element in the set of the range. Okay, I will be back. Okay guys, that's all what I had for you. Just to read once more, a function can also be pictured as an arrow diagram, just as we have it in here. Each associates an element of the domain with a unique single element of the set of Y. The arrows indicate that f at a is associated with a, so the value of a give you the value at y at that point. F at x is associated with x, so the value of y corresponds as a result of the value of x. Notice that a function can have the same value at two different input elements in the domain, as occurs at f at a. Now let's read this. Very important. Notice that a function can have the same value at two different input elements in the domain, right? But each input element x is assigned a single output value, and we will demonstrate this very much when we are doing the problems. As you can see here, we have an x value from the set of the domain, and it has a corresponding y value. And what they are saying here when they say that, notice that a function can have the same value at two different input elements. It can have the same value. So y can have the same value at two different x values. So we can use two different x values that can give us the same value of y as in the diagram here. Hence they are saying, notice that a function can have the same value at two different input values, and we will deal with this in the second tutorial.